Hello everyone! So right now we are going to talk about the Pythagorean theorem and special right triangles. But before we get into the problem sets, or actually this is the first problem I believe, we're going to prove the Pythagorean theorem because I am a huge fan of proofs. So for those of you guys, none of them know how, but we'll teach you guys now. A, B, C. You have a right triangle like this. A squared plus B squared is equal to C squared. And we're going to prove that using this sort of complicated diagram that we have above. We are going to figure out the area of this huge square using two different methods. And then along the way, we're also going to prove that A squared plus B squared is equal to C squared. Well, the first way that we can get the area of this square is by taking base times height, which is A plus B times A plus B. So this is equal to, or area is equal to plus B squared. That's equal to A squared plus 2AB plus B squared. Another way we can solve for the area of this thing is by counting these tiles individually and then counting this big square here. And I know I didn't really draw as a square, but I swear the area of this is C squared, base times height. This is supposed to be a square. So, and the areas of all of these small triangles, well, that's AB divided by 2 times 4 of them, so it's just 2AB. So this is also equal to C squared plus 2AB. And we know that these two equations both get us the sum, I should write a big A, the area of this huge square here. So we can subtract 2AB from both of the equations to say that A squared plus B squared is equal to C squared. And this is one of our more basic proofs. There are a lot of proofs of the Pythagorean theorem, by the way. I encourage you guys to watch videos on them on Khan Academy, but this is generally the easiest one to solve because we already have a really good setup here. Alright, so that's problem 5. Problem 6, we're going to be talking about Pythagorean triples. Pythagorean triples. A Pythagorean triple is an ordered triple of positive integers a, b, c, satisfying the equation a squared plus b squared equals c squared. Okay, well, that makes sense. If x 28, 53, and 13, y 85, and z 20, 29 are all Pythagorean triples, what is the greatest prime factor of their sums? Alright, well, let's figure out what x, y, and z is first. So they all satisfy this equation, a squared plus b squared equals c squared, and it's an ordered triple. So if we start with this set here, x, 28, 53, this set of numbers, we know that x squared plus 28 squared is equal to 53 squared. So with that, we can figure out what x squared is. Then we know this here, 13y 85, 13 squared plus y squared is equal to 85 squared. Then we have our final set, z 20, 29, and z squared plus 20 squared equals 29 squared. It's kind of, I wouldn't say that you should memorize Pythagorean triples, although you should memorize the most basic ones, mainly 3, 4, and 5, and just 5, 12, 13. Yeah, and you can also, by the way, you can also multiply them by 0.2 to get 6, 8, and 10. But you don't actually memorize this. These two, I would say, might be the most important ones. But generally, you could also just use a Pythagorean theorem. This kind of saves you time. Actually, moving on to these equations, sorry. So to figure out what x squared is, we want to get 53 squared minus 28 squared is equal to x squared. A fun thing we could do, and a easier way to do this, instead of actually figuring out what 53 squared is and subtracting 28 squared from that, we could say that this up here is equivalent to 53 minus or plus 28 times 53 minus 28. And if you guys will recall, this is kind of the same formula as this here, a plus b times a minus b is equal to a squared minus b squared. We're just applying it to these numbers so that we can calculate things easier. Okay, so 53 plus 28, that's 1. Carry a 1, that's 81 times 53 minus 28. That's equal to 53 minus 30 plus another 2. So, okay, sorry. That's equal to 20 to 25. So now you have 81 times 25 is equal to x squared. And this is where I try to like expedite the process for these for the calculator work. But if you guys are actually doing this problem, you guys should do it by hand, get better at arithmetic. 81 times 25, 0.25 is equal to x squared. X is equal to the square root of that, which is 45. So we know that x is equal to 45 up here. Then we could do the same process for this here. 85 squared minus 13 squared is equal to y squared. I'm actually just going to, after like teaching this trick up here, just going to subtract them by calculator. 85 squared minus 13 squared, square root of that. That's 85. Y is equal to 85. And for z, 29 squared minus 20 squared is equal to z squared. Z is equal to 21. Okay, so we have what x, y, and z is, but that's not the answer, of course. We're trying to find the greatest prime factor of their sum. So we have 45 plus 85 plus 21. That's equal to 1, carry a 1, yeah, 151. Oh, sorry, wait. Did I? 45, 21. Oh, sorry, I miswrote this. This is supposed to be 84. Sorry, I miswrote this. You know, funny thing is the calculator, I mean, you can get the answer from the calculator, but it doesn't work if you write it wrong. This is actually 84. So writing 84, and this is equal to 150, and we're trying to find the greatest prime factor of 150. So, to find the greatest prime factor, we just factorize it, completely factorize it. 150 is, well, I'll draw a factor tree. Let me erase all this work here. 150 is equal to 5 times 3, which is equal to 15, times 10, which is equal to 2 times 5. So that's equal to 10. So the complete prime factorization is 5 squared times 3 times 2. And the greatest prime factor in this is 5. So our answer would be 5. Okay, that's problem 6. Whoa, problem 7. Find the length of the altitude to the base of an isosceles triangle whose base is 16 and legs are each 10. Okay. Well, we have an isosceles triangle like this, whoosh, like so. The base of an isosceles triangle is 16, and the legs are each 10. So we have a triangle that looks like this. And an altitude is kind of a line that drops from an angle, like this angle here, down to the base. So we'll draw it like so. The thing about isosceles triangles is that their altitude meets this in a perpendicular line. So this is actually a 90-degree angle. And because this is 90 degrees, we can use the Pythagorean theorem to figure out what we want. Oh, by the way, it also bisects the base. So in total, the base is 16 units. But each of these over here are both 8 units. And what we want to figure out, I believe, is the length of the altitude. So we want to figure out this. So what we would do is 10 squared minus 8 squared is equal to a squared. And then we would just calculate. But if you remember your Pythagorean triples, you'll recall that 3, 4, 5 is a Pythagorean triple. Multiply both of these numbers by 2 and you'll arrive at 6, 8, 10, which are the numbers that we need here. So A is actually equal to 6. We can do that without calculating this. Alright, that's problem 7. Oh, problem 8 is the hardest one. Okay. Next problem, problem 8. Oh, I sure hope I've been recording. The midpoints of a regular hexagon are connected to form a smaller hexagon. What is the ratio of the perimeter of the small hexagon to the perimeter of the large hexagon? Okay, well, let's try to draw a hexagon. 2, 3, 4. Hexagon is 6 sides. Right, I'm pretty sure. Okay. So our hexagon, A, B, C, D, E, F. And we are connecting their midpoints. So here, 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 and here. Oh. Did not need to draw this line. And I'll call this midpoint C, G, H, I, J, K, A, B, C, D, F, G, H, I, J, K, L. And because we know that this is a regular hexagon, that means all the side lengths are equal. And I would call let's call the side length of the larger hexagon L, the side length of the smaller hexagon S. And we want to find the ratios of their perimeters. The small hexagon to the perimeter of the large hexagon. Well, the perimeter of the small hexagon, that's 6 sides, right? So it's 6S to the perimeter of a large hexagon, which is 6L. And remember, S represents small, L represents large, and both of these variables represent the length of these sides. Well, we can simplify this ratio to say that we're only trying to find the ratio of one of the side lengths of the smaller hexagon to the side length of the larger hexagon. So we just need to figure this out. Okay. Well, what we can do about this is that we can kind of draw, a diagram. Well, first of all, we can figure out the angles of one of the larger hexagon. So the thing about regular hexagons like this is that there's a formula to figure out the sum of all the angles, and that formula is 180 times n minus 2, where n is the number of sides. And you'll see that this works for triangles too, right? So triangles have 3 sides, 3 minus 2 is equal to 1, 180 times 1 is equal to 180, and the angles in triangles sum to 180 degrees. Well, we can use this for hexagons too. Instead, our equation would be 180 times 6 minus 2, and that's 180 times 4, and that's equal to 720 degrees. And then we can divide this by 6 because it's a regular hexagon. There are 6 angles, and all those angles are equal to each other, so 720 divided by 6, and that's equal to 120. 120 degrees. So for this right here, AGH, I'm kind of going to zoom into this. For AGH, we want to compare, right, so we have this here and this here. We have a 120 degree angle here. And we know that this is an isosceles triangle too. These two angles are congruent, so we can figure out what these two angles are. And these two angles is equal to 180, it's still a triangle, minus 120 divided by 2. So that's each of these angles are 30 degrees. And like we discussed before, we can also drop an altitude down here like this, making a 90 degree angle. And so instead of 120 degrees here, we just have a 60 degree angle here, and a 30 degree angle here, and our right triangle. And so there's a special property of 30, 60, 90 degree triangles that I hadn't mentioned before, but I will mention now. The property of 30, 60, 90 degrees triangles is that we can figure out their sides without using sine, cosine, and the rest. You can just kind of remember this. 30, 60, 90. The thing about 30, 60, 90 degree triangle is that it's half of an equilateral triangle. So if you kind of visualize this, it makes more sense. 30, 60, 90. All of the angles of an equilateral triangle are equal as well. So this is 60 degrees, 60 degrees. 30 plus 30 is also equal to 60 degrees. Then we can label the sides. So this side, let's say that this side is x. Well, if this side is x, this side must be 2x because all of these sides are equal, right? And this is half of one of the sides. So this is 2x. And then with the Pythagorean theorem, we can figure out what this side is. And it turns out that we get 2x squared. Put the parentheses in the wrong place. 2x squared minus x squared. You get 4x squared minus x squared. And then you get 3x squared. That's the side of this. But then you also have to find the root of this. So you get x root 3. So in our triangle, in a 30, 60, 90 degree triangle, we can figure out the sides immediately, knowing one of the sides. Let's say that this is 30 degrees, this is 60 degrees. This is supposed to be the longer side. Oh, yeah, I'll try to draw that better. Okay, this is the 30 degrees, this is the 9 degrees, this is 60 degrees, this is x squared root 3. This is x and this is 2x. Alright, so now that we have, so here we also have a 30, 60, 90 degree triangle. And we can kind of just name one of the sides. So let's say that we're going to define AH. And we're going to define AH to be, let's say we'll define AH to be 2x. Just for simplicity's sake. And by the way, we were trying to find the ratios of these two hexagons, so it doesn't actually matter what their actual lengths are, because this is about proportions. AH will be 2x. And so because AH is 2x, we know that this is x squared root 3, and this here is x. Alright, and we know that the length of one of the sides of the larger hexagon, so this side here, AB, is 2x plus 2x, so one of the sides is 4x. L is equal to 4x here. So now we're trying to figure out what S is, and S is this here. Well, we know one of the S, we know half of the S is x squared root 3, and we know this other half is also x squared root 3. So x squared root 3, so 2 times x squared root 3, S, well 2 times x squared root 3, that's equal to 2x squared root 3. Okay, now we're trying to find the ratio of S to L, so it will be 2x square root 3 to 4x, and then you can divide by x on both sides, and then you can divide by 2 on both sides, so then you get square root 3 to 2, I believe. Yeah. Oh, instead of like writing this as this ratio format, you can also write it as a fraction format. Square root 3 divided by 2. And okay, and that is our final ratio. And you'll notice it doesn't actually matter what the side lengths actually are, and they don't tell us what the side lengths are, so I just use variable x. You can figure this out without figuring out what the side lengths are. It's just a ratio. And thank you guys for watching. Remember your remember your isosceles triangle properties. You can memorize some of the Pythagorean triples, mainly 3, 4, 5, and 5, 12, 13. Memorize the properties of special right triangles, such as the 30, 60, 90 degree triangle. That one's important. Try to memorize this format here. And also memorize that properties of isosceles triangle. That's also important. So you can drop an altitude like this, and it will be 90 degrees if this is an isosceles triangle. And the legs of an isosceles triangle are congruent, and if the angles of if the leg angles of the isosceles triangle is congruent, this is also congruent. If you know what I mean, I kind of worded that poorly. And I think that's about it. Oh yeah, also properties of degenerate, non-degenerate triangles. And you'll notice that we didn't actually talk much about acute and obtuse angles, though they kind of show up. They don't actually show up that commonly. Oh yes, remember how we derived the Pythagorean theorem? Well, I find that it's kind of difficult to forget that formula. And yeah, we'll see you guys next week. If you guys have any questions about your problem sets, remember you can email us or talk to us in Google Classroom. Whoosh.